Hey there, calc folks. A little quick peek behind this, the scenes here in my studio space. Always a treat to see perhaps where I'm working from. But I'm back here with another quick video over some application of integration, the integration process here. Where we're going to look at what's known as the general slicing rule. And what the general slicing rule is going to lead us into is what we call the case for the volumes for solids of revolution. There's going to be some methods for calculating the volumes for what we know as, or are going to learn about, known as solids of revolution, using what we call the disk method and the washer method. Right, in those calculations. And what's going to support the disk and washer method is going to be this idea behind the general slicing rule. All right, so what we have here is really just another idea that builds itself upon the integration process. There is some underlying theory that we're kind of skipping over for the moment. We're not really looking at the proof of these formulas. My hope is to come back in just one lecture video and give you that proof. So that I don't make things longer than they have to be in some of just these introductory videos. So, I am foregoing a bit of proof for the moment, but my hope is to come back into a video where I kind of summarize all the proofs in one video. So the proof of some of these formulas will appear in that video, folks. So not to have to place that idea into this and just make the ideas longer. My hope is to make these videos just shorter so they're easier to manage overall. But here, as I noted, we are going to be looking at the general slicing rule, and the general slicing rule is just another application of integration. And what it's used to define the volume of is for a solid that forms in three-dimensional space along a particular axis of that space, we say. Usually, we might set the problem up so that the solid forms along the x-axis. But certainly, this solid can form along any of the three axes that describe our three-dimensional space. What has to be unique, though, to the setup is that if we looked at the cross-sections perpendicular to the axis along which they're forming, where in our definition here, our idea, our rule, we consider that to be the x-axis, at any value of the variable along that x-axis in some closed interval, in our case for x in this interval from a to b, we have the area of that cross-section described by the function little a, or the function big A of x. If we know how to find the area of the cross-sections perpendicular to that axis over which the solid is forming, over some interval of the variable along that axis, this value we might describe by the value a of x, then the volume for that solid, right, that forms over those values of x in that interval from a to b is going to be described by just simply an integral from a to b for our area description with respect to that variable x in this case. All right? If we were to form along the y-axis, it would happen with respect to y, and the setup would all be with respect to y. Or if it was to form vertically in the space along the z-axis, this would all be relative to z, right, in the calculation. Now, I do have a visual illustration of this volume that we are generically describing here. We might say our volume looks something like this. Here we have, in this illustration, I might make it a little larger so we can see it here, a little clearer in the video. All right, here is our solid of revolution. It's this light bluish gray solid forming in this three-dimensional space. And we can see that this three-dimensional solid forms along this x-axis. Here's the x-axis in that space. From x equal to a is where the back end of the solid is in this space, up to this value where x equal to b, this front end of the solid is forming us in this space. And we can see that the base of the solid might be this trapezoid that's down here in the xy plane, and this whole solid is forming over that trapezoid with with this curvature we see here being illustrated across the top of this solid. All right. Well, the solid does form along the x-axis, where what we have to assume is that we know, right? One of the assumptions we have to make is stated down below here, is that we know the area of what would be the cross sections perpendicular to this x-axis. Now, in this illustration, those areas that are perpendicular to the x-axis, I do have a couple of them here represented in this illustration. Here's the first one that's occurring at x sub 1. Right? Here's the second area that's occurring at x sub 2. And what we have to assume in this setup is that we know how to calculate the area at any value of x for one of these particular cross sections. We must have some sort of formulaic way of describing that area, either given to us explicitly in the problem or given to us through the description of the shape and how its dimensions relate to x, or, yeah, it can be a bit of a puzzle at times to try to figure out a of x. All right? But here we have this illustration of our solid forming in this manner. To help us see the solid a little clearer, if you're having a little hard time seeing that solid, I do also have its illustration here in Mathematica. Let me go ahead and flip over to that just to show you this solid in Mathematica too. And what's nice about the solid in Mathematica here, to begin with, here is the program I programmed out in Mathematica to just make this solid happen, folks. So this is sometimes what slows me down in getting these videos out to you and these lectures put together, is it's putting together some of these illustrations. That's quite a few lines of code to make this illustration. And that illustration is not even really that dynamic. What is interesting, though, in it is I can rotate it around in space. So that's kind of nice. I can do a little rotation here with it, and you can kind of get a visualization of what that solid might look like, and I can stop at any point. And there we are again. There's that solid forming along the x-axis again. We can kind of still see that curvature on the top. It's forming over this trapezoid down below there, and there are those two cross sections again at those values of x1 and x2. We could even start to look at the solid from this side, right? From that back end side, and we can see how that solid is forming in that space. And if I was told some formulaic value for a of x, what describes the area of these cross sections with respect to the values of x over the x-axis from a to b here where they are forming, I would be able to come up with the volume for this solid. All right. Certainly. That's not, in general, we assume that is given to us here, and that is what the general slicing rule requires in its calculation, right? It does require that we have that description of the cross sections perpendicular to the axis over which this solid is forming, all right? And sometimes that is given to us, sometimes it's we know the shape of the cross section, so we have to have some way to then to relate the dimensions of that shape to the value of the variable over x, for instance, the value of the variable over which the solid is forming, right? The corresponding to the axis over which the solid is forming. Or at times it can just be a bit more of a puzzle to form that formula. All right? But let me give you an intermediate example here. I don't give you the formula explicitly, but I do give you here this situation where we consider the volume for the solid forming along the x-axis over x in the closed interval from 1 to 3, right? Where we're told a little bit of information about these cross sections. We're told the cross sections perpendicular to the x-axis are all rectangular in shape. Now, knowing a little bit of information there about their shape, we can say a little bit of information about their area. To begin with, knowing that they're rectangular in shape, we know to find their area might require us to look at the length of the rectangle times the height of the rectangle, or times the width, depending on that dimension, how we want to summarize that. Right? Here, we're told a little bit about those dimensions, and we're told about those dimensions in the context of x. Right? They're all rectangular in shape, such that when we think about the length of these rectangles, right? They're all measured 2x minus 1, depending on where they happen at along the x-axis from A to B, right? Their measurement would be 2x minus 1. If we say we're looking at x from 1 to 3, maybe they're happening at 2. So what would be their length at 2? Well, their length at 2 would be 2 times 2 minus 1, or 3 in value. 4 minus 1 is 3. As for the height is described by the measurement x plus 1. Again, referring back to its location along the x-axis. And if we were again at the value of 2, what would be the height? The height would also be 3. So the area of that one little triangle, that one rectangle that's occurring at that location in space would simply be 9 units. It would have 9 units in length, and it would have 9 units in height, and it would, or 3 units in height, 3 units in length, so it would make 9 units squared in its area. And that shape, or those cross sections, vary with respect to x based upon this relationship, 2x minus 1 and x plus 1 respectively. All right? So if we think about just the area in general, right? In this case, the area of the cross section, right? Since rectangular in its shape, right, are described by, in this case, the area of the cross sections, let's make that plural, since rectangular in their shape, right, are all described by the function a of x, where a of x comes from that length times that height measurement, where depending upon the value of x, length is 2x minus 1, and depending upon the value of x, height is x plus 1. So length times height would be 2x minus 1 times x plus 1. And that would be the function of x that describes the area of all the cross sections, right, perpendicular to this x-axis, this axis over which the solid is forming, right, on this interval from 1 to 3. Right? So, right, in the volume calculation, right, the volume of the solid is given by the integration seen below here. It is the integral of this area function over this interval from 1 to 3 with respect to x. It is this integral from 1 to 3 for the quadratic, 2x minus 1 times x plus 1, all integrated with respect to x. Right? That quadratic there has been factored. Realize to actually perform the integration here, we may consider expanding this integrand into a nice polynomial. What would that be? 2x squared plus x minus 1. Right? So I could expand this into the polynomial, or the quadratic, 2x squared plus x minus 1, rather explicit here now, where we can integrate it across this interval from 1 to 3 using the fundamental rules of integration here, a little sum and difference, constant multiple, and power rule. That does give us 2/3 x cubed, right? Bump it up to 3, divide by 3, plus 1/2 x squared, bump the x up to power 2, divide by 2, minus x, right? This is x to the 0 times 1, so that would be x to the first divided by 1, which would just be negative x times that constant multiple of negative 1. So now if I evaluated it at the upper bound of 3, this would produce 18 plus 9/2 minus 3, that would be 15, right, plus 4.5, so that would be 19.5 here, right? Minus this quantity here, what I'd get if I substitute in, I have an error in there. 2/3 plus 1/2 minus 1 in value. All right. Now I did calculate this out and check that down below here in Mathematica. I did do this calculation check in Mathematica. I did not see my error here though. I based that off of this calculation, so it should be correct down below here. But this then would be 2/3 plus 1/2 minus 1. Let's just see what that would simplify to. Certainly these are all sixth in their lowest terms. This would be, what is that? 4/6 plus 3/6 is 7/6 minus 6/6. 7/6 minus 6/6 is 1/6. So really this is 19.5 minus 1/6 in value. And you can see there that's going to be a little under 19. And that's what 58 thirds is. It's a little under 19, so it does seem to check without a heavy check on that. It seems appropriate, right? Thus, the volume of this solid is 58 over 3 units cubed in its measurement. Now notice, folks, here, I did not sketch the illustration of this solid. You could certainly attempt to do that. But what I did depend upon was a little understanding about the shape of that solid, that being rectangular in shape, right? I'm noting that, well, from my geometry experience, the area of a rectangle is calculated using length times height, and relying upon the measurements that we have for length and height in terms of x, I was able to set up that area function a of x down below here. And the calculation is nothing more than an integral over this interval of x for which the solid is forming along, right? This interval from 1 to 3. Now, again, I did not give you much proof here, but if we were to justify this just a little bit, folks, again, we go back to that idea that what is an integration, right? Certainly this is a net area calculation if we were just to think about it'd be the net area trapped between the area function and the x-axis for values of x from a to b, right? What is it actually doing, though, in terms of this volume calculation is we are taking this quantity a of x, which is the area of all the cross sections that are occurring at each and every value of x on this interval from a to b. All right. How many of those cross sections are there on this interval from a to b? Well, there's an infinite number of those cross sections. So in a sense, there is an infinite number of slices, right? What we really are doing is thinking about having this volume sliced up along the x-axis, where we can figure out, based upon the given information, what is the area of each slice with respect to its location along the solid, right? Along that axis on which the solid is forming. And if we take each and every one of those infinite slices area and we add them up, right? Those would all accumulate, right? Each and every one of these areas, these are just two of the infinite number. Each and every one of those infinite number would accumulate and actually make up the solid itself. If I was to visually illustrate each and every one of those areas in this picture, it would be that entire solid in its illustration, right? This solid illustrates each and every one of those infinite areas. So if we add up all those infinite areas, we would have, in a sense, the volume that solid is forming. Now, we can't add up an infinite number of items, so how do we approach that? Well, we approach it using a limit, all right? We approach it using this integration process. Remember, the integration process summarizes the application of a limit to a summation, right? We look at the sum of the patterns formed by slicing the solid into, or I should say here, slicing this interval from a to b into n subintervals, which in turn slices the solid up, right? Where we can then think about those, that solid as n heads off to infinity, the number of slices we slice the subinterval from a to b into, if that heads off to infinity, we're going to see this behavior in the area function develop, right? This behavior that for the summation of the area function develop, that we can explore its behavior as the number of slices head off to infinity. And that is the integration process in summary, right? Or is as defined, the definite integral process as defined back in chapter 5. So that's a little bit of the proof, a little bit of the theory here. We are summing up an infinite number of areas, right? That's what this volume is calculating, is the sum of an infinite number of areas. Folks, certainly we will, though, come back and look at a bit of proof here for some of these in the future and kind of formalize what I had just explained there. But I want to keep these videos short. Here we're right on the 20-minute mark. So I will end with that. But where this is leading us to, folks, is disk and washer methods. which are general slicing rule applied to a more specific case known as the case for a solid of revolution. All right. So we will come back to that, or those two ideas here in the next video, which I don't know if I'll have together for you tonight, but you should see here shortly in the next day or so. All right. So with that said, I will sign out, and I'll see you all next time.